So, well,
without further ado,
thank you
thank you
very
very
much
much for coming here.
It's a pleasure to have with us today Trevor Canham, whose mic just fell off. That's being recorded, sorry. We'll edit that out.
So Trevor was born and raised in Rochester, New York, and where he studied a degree in motion picture science. And we've been working together since 2017 or 18. 2018 in the context of European projects on media production. And he is now affiliated with Psychophysical with us. And he will be speaking today about the work we've been carrying out with Javier Portilla and Martín that deals with the photorealistic style transfer. So thank you very much, Trevor. The floor is yours.
Thank you, Marcelo. I'll get right into it. So this presentation is related to a paper that's in progress, which we've titled Using Decoupled Features for Photorealistic Style Transfer, which Marcelo mentioned is in collaboration with Adrián, Martín, Marcelo, and Javier. So just to give a bit of background on style transfer and the application that we intend to use it for, a really early digital intermediate color grading success was the Coen brothers film Oh Brother, Where Art Thou, where the film negatives were scanned into a digital representation and the colors of the foliage were targeted to shift them from appearing lush and green towards something more dry and more like a drought. And this really showed the cinema industry the promise of using digital color grading. It showed a very clear example of something that digital color grading could do that they couldn't do previously with film color grading. And around the same time, Eric Reinhardt introduces a method for style transfer for this application, for a similar application, where a reference image, here the example is his source image is a dry scene. This is the top left. His reference image is a lush scene, and he uses a transfer of the statistical moments of mean and standard deviation to achieve this sort of lush version of the dry image. And here's just an example of the Oh Brother, Where Art Thou color grading effect. So this is sort of the context of the ideas that were going around at the time when these methods first started coming about. And Reinhardt's method was very robust and easy to use, but it wasn't so exciting. It was sort of what you see is what you get. You can sort of imagine how the mean and standard deviation of an image would look when applied to another one, and a lot of times this was sort of lackluster. It didn't have this sort of alternate reality effect that people were hoping for in the context of these other color grading successes. So moving forward, Morovich and Sun used optimal transport to transfer color between groups between a source and reference, similar colors. So optimal transport is a field of study that came about in the industrial era for transporting resources to factories, and then people took those models and applied them to any given data set. In this case, it would be one set of colors and another set of colors that were meshed together, which allowed for a bit more of an alternate reality effect, but still didn't touch texture or anything, still was strictly limited to color. And also, from the examples we have here, on the left is the reference image, and then these are three results that are sort of matched to it from other things. And I know you can't probably see very well from where you are, but the results often are really blocky. They have a lot of banding and color artifacts. And we still see that today. We'll go over that as well. Moving along, Gattis introduced the concept of neural style transfer, where convolutional neural networks were used to transfer higher level features between source and reference. And the very successful case was the idea of taking renowned painters' styles and applying them to any given source image. So we see a couple of examples of that here. And this created a lot of excitement and momentum in the field, which carries on still to today. So we see neural style transfer being applied in the very heavily marketed DALL-E and Midjourney systems, where people can introduce text inputs, and in addition to a module for locating and masking out recognized objects in the source and reference images, they use a style transfer method to bring them together and put them in the same context. So, like I said, the area has tons of momentum, but it still has serious problems that we saw then with Gatis, and we still see now with these modern iterations. Which the other problem for our application is that this is sort of overkill for color grading. If we're really just trying to replicate the photographic or color grading style of a reference image, then we really don't want there to be, new synthesized elements of the image, or these, surreal sort of elements being introduced. And also, even to do the simple task, we want, these very complicated models that we don't understand very well how they work are just not quite good for our application. And we'll go into that and provide some examples from some more recent iterations of these sorts of methods moving forward. But for color grading, I would posit that nothing has reached the robustness and usability of Reinhardt. So for our method, we expand upon the idea of Reinhardt to include further statistical moments and features that were previously not available to us for transfer. So just to give a bit of an overview on statistical moments, I know that our audience here is probably well versed in statistics, but just to give an overview, I have as a visual tool, I have an image histogram here. So the mean and standard deviation are the two statistical moments that Reinhardt used for this method. And you can think of, by matching the mean to a reference image, you're sort of doing a translation on the histogram. Whereas matching the standard deviation, now you're sort of stretching the histogram laterally. And these two statistical moments kind of have an effect over the whole histogram. They don't really have a localized effect over one side or the other, or any of these individual regions. So, and they correspond to the perceived brightness of the image and the perceived contrast. So those are a good first start. You can see here some examples of our method where we go further with more statistical moments, but we'll just limit now to the first two images in each column, or the first three rather. So there's the source, and we're matching to the target on the other side. And we can see if we apply the mean, we get a very big change from applying the first one. This is to all color channels as well, so per color channel mean. We can see that we start to move very much towards the average color value of the target image there. And then by applying the standard deviation, we start to get some of the contrast elements as well. A good example probably are these two rows on the bottom. You can see from this image to this image, we start to get more contrast in the sky, which matches the contrast elements of the target image. But there are further moments which are also useful, although the effect of working with them is more subtle. And those moments are skewness and orthokurtosis, which I'll summarize with the histogram by meaning skewness refers to the degree to which the image histogram is shifted towards the shadows or highlights, whether the balance is skewed skewed towards one side or the other. So this is how you get the skew value. And most images in cinema, for example, would have a negative skew value, where there's more shadows than highlights, which you see in this diagram here. So now, by touching skewness, we start to get sort of a more localized control over the different image regions. And kurtosis goes even further, or orthokurtosis goes even further to describe whether there's a large concentration even further towards the blacks and whites. So by being able to decorrelate these two statistical moments from each other, we give colorists the ability to adjust the blacks and whites separate from the shadows and highlights, which is really useful, particularly with novel technology like high dynamic range, which extends the range of reproducible light values in the image. And in that extension, these tools which touch the mean and standard deviation value, because those values sort of correspond to the whole image histogram, they're not as useful in the case of high dynamic range, because high dynamic range presents the challenge of needing to adjust those image regions on a more specific basis. Basically, they're too heavy-handed. If you touch the mean of an HDR image, it's useful, but you're going to, since you have all this extra detail in the shadows and highlights, you're going to want to be able to touch those on their own. And the other reason why these moments are really useful and relevant are that they're very important to visual adaptation processes. So we know that visual adaptation centers itself around statistical moments. Like, for instance, brightness adaptation is going to center itself around the mean in order to encode visual information efficiently. By making the mean value a coding value of 0, you're taking the image value that's the most common in the image, and you're using the least amount of energy to translate it. So mean is a really important parameter for visual adaptation. Standard deviation is also very important for contrast adaptation. And moving along, these other moments, skewness and kurtosis, have an adaptation importance as well, for instance, in the visual cortex. So for this reason, we felt it would be useful to be able to decouple these statistical moments and transfer them in a style transfer context, which was not previously possible before the work of Javier. So this is the core of our style transfer method, is to be able to decouple all of these statistical moments from each other and adjust them. And it does that by normalizing each individual feature and then searching for a function along a consistent decorrelated pathway which achieves the target feature while impacting the image in the most minimal way. And this is really useful for us because by stipulating that, we're avoiding many artifacts, or we're avoiding artifacts as much as possible. More specifically, in terms of the color representation, we're transferring the mean and standard deviation on all color channels in an ITP space where I corresponds to luminance and T and P correspond to chroma values. So we do the luminance and chroma for mean and standard deviation, and then we opt to just transfer for luminance the skew and orthokurtosis because we found this was the most robust configuration at the moment. So in what follows, we'll justify our design decision of pursuing the statistical transfer idea of Reinhardt by comparing to optimal transport, neural style transfer, and some other methods in context. Oh, and I should point out, so applying the skewness and kurtosis are probably very subtle. Let's see if there's anything that we can see Okay, the third row here is probably the best one. So you can see the transfer is really subtle, but it starts off with more of a red color balance. Then matching to the city image, it gets more blue. Then matching the higher contrast of the city image, the clouds are brought up. And the skewness brings those clouds up even more. But you can see that it clips out a lot of the detail. But by using the orthokurtosis, we're now separating sort of the whitest areas from the highlights, and we see that we can get some of that detail back there. So adding these additional statistical moments are sort of a refinement step, which is really important for color grading. So looking at the methods of optimal transport, as we said, optimal transport tries to find the most efficient transfer of color values. So it basically matches the most similar color regions of the image together. And we can see, compared to our results in the third column, the results of Rabin, Faralans, and Blondel are quite a bit more blocky. There's quite a bit more banding artifacts. And the other thing is that a lot of times these methods don't find an optimal solution to make the transfer, and then you end up with image regions that are completely unrendered. And this is just using the demo software that they made available. This is still sort of quite a popular use of, or a popular method for achieving style transfer, but we still have the exact same problems that were seen with Moravich and Sun. Obviously, people are doing things to introduce smoothness coefficients and so on to improve these artifacts, but they're still here. So we didn't feel that would be a good route to go down for style transfer. Neural style transfer identifies low-level image features via a convolutional neural network and matches between similar ones. So Luan, in the third or fourth column, was a very popular example of photorealistic neural style transfer. It was one of the first neural style transfer methods to actually show usable or presentable photorealistic results, whereas most other ones were, just to clarify the meaning of photorealistic, many other ones were putting output in a painterly art style or something like that, which is, I mean, you can have photorealistic painting as well, which sort of confuses the definition, but they weren't producing results which you could look at and say, oh, this is a photo of a real thing. So Luan sort of really made a big splash with his method in that sense. And moving forward, Lee and Mekrez add refinement steps to a very similar or the same process as Luan, or they just take the output from Luan and apply a refinement step. In the case of Lee, it's sort of a smoothing step, and in the case of Mekrez, it's sort of like I guess like bilateral filtering step where it smooths out solid blocks and then sharpens edges. We also include the method of Huang, who offers, whose method is intended for the field of image translation, which is slightly different from style transfer, but in the sense that in image translation, you're trying to transfer higher level properties. For instance, like you'd want to turn a picture of a dog into a cat or something like that. Or you'd want to take, a real image and turn it into a nice like line drawing style or something like that. But in their paper, they also demonstrated that they could produce photorealistic results with their methods. So we include them here as well for that and for the sake that they're extremely popular. However, if you use these images in the way our users would without retraining them for a specific data set, since this can be really time consuming and energy, can cost a lot in terms of energy and money, obviously, you get results like this, which include a lot of spurious artifacts, these sort of surreal things I was talking about. in all of these examples of Luan, you can see large parts of the images which sort of get blurred out or become a cloud, or there's some weird things happening. And then from there, the smoothing operations or the refinement operations sort of just put like a nice mask over that, but they don't correct what's happening here. And that's really a primary problem with these methods is, first thing, they're not robust outside of their training set. The second thing is they have a high cost to train, which I mentioned. And the third thing is that they're black boxes without human readable parameters, which makes them really bad as creative tools. The most essential element of a creative tool is that somebody can go back and learn to work with it and learn to refine it and refine the specific things that it's doing. Whereas in this case, it's outputting things that would be more work to correct than it would be to just do the operation manually in the first place, in our case. So obviously, it's no good for our application. But since a lot of machine learning research is mostly disseminated to the public through marketing channels, since a lot of the research is being done by corporate entities, these sort of problems don't get mentioned. And we still have things like DALL-E and Midjourney, which are very popular, that have a lot of problems, and people are writing articles about it like it's the apocalypse or something, like it's the end of the world and it's too dangerous to be unleashed on society or something like that. So the result of this sort of thing we have going on is overhype, and it's sort of leading the attention away from the development of tools in this field for parties with high quality standards like the workers in cinema and photography. So moving on, there are some methods which are more appropriate and marketed towards these fields, which we highlight here. So the first one we highlight is that of Grogan, who homogenizes the colors between a source and referenced image to minimize an L2 divergence cost. There's also the method which is made available in Photoshop today. It's the only actual commercial style transfer method for in a photo editing platform that we are aware of. We can't say how it works, obviously, it's closed, but we can obviously test it, and we have here. And also we test the method of Fabaleta, which combines a constrained histogram equalization step to match luminance characteristics between a source and reference image. Then it makes a match between principal components of a color cloud and makes a local contrast transfer to match between a source and reference image. So in these methods, the artifacts are still present, but they're fairly minimal, they're correctable, and they're natural, I'll say, in the sense that they're the artifacts that a colorist may come across in their workflow, not like these, which, you know, artifacts like these would never happen from a color correction tool. But these artifacts are more clipping. They're more related to clipping and banding and things like that, which our colorists are used to. And if you're working in a non-destructive format, you can pull back on those and get detail back. So we went on to conduct a psychophysical user study to compare the results of these methods, which we'll get more into the differences between them in relation to that. So we conducted an online experiment, which I'm doing a quick demo of here on the screen, where observers were presented with a style image on top and then two results of two style transfer methods compared to each other. And their task was to select which of the style transfer results they felt best reflected the style of the reference image, and the one which they best preferred had the least artifacts, and so on. So for this test, we used a combination of 5 highly chromatic stylized and JPEG compressed images in an 8-bit format, which are the same images I've showed on the last 3 slides. And these represent very much like a challenge case for style transfer, because they're the most likely that you're going to run into banding artifacts. They have the strongest style components, so it's quite easy to see whether they're working or not, for instance. And we tested every combination of the 4 methods that we presented previously, which are our method, the method of Grogan, Photoshop, and Zabaleta. So it ended up as a 120 trial experiment, which lasted around 10 minutes on average, which is well within the range of observer fatigue. And observers were of varying ages, genders, and nationalities. Since it was online, the displays were in the wild. We had no idea how they were calibrated, but we stipulated that observers should run the experiment in a dark viewing environment. And on to the results. So the results from this experiment put Photoshop last, then Zabaleta ours, and gave Grogan the best results. However, the per image results here, which compared between Photoshop, Grogan, ours, and Zabaleta, showed that we were the most robust to extreme failure cases. And we believed that the experiment failed to communicate the working context of using these methods, in the sense that since the source images were not shown, observers couldn't judge the faithfulness of the result to the original image. The Grogan method, we believe, won because it basically snaps everything to the average reference color, which we show some examples of here. So these are the Grogan results, the source, the Grogan results, and our results. And you can see in our results, we still maintain some differentiation between the background and the foreground, particularly this skin tone here. Whereas they've really made it sort of a monochromatic image, which you could imagine as someone's flipping through an experiment trials, and their task is to judge which best reflects the style. This is sort of the simplest representation of the style at first glance, but this is problematic because it removes, by being destructive to the discrimination between color elements in the scene, for instance, skin tone and background, it takes away the colorist's ability to control image regions based on color, and also throws away important color details like skin tone, which is not desirable. So, in response to this, we're redoing the experiment with the simple change that the source image is included, and we have some additional instructions detailing this difference in context. So you can see now we have all 4. On the top left, you have the source, reference, and then the 2 results. We believe observers will be closer to the color grading context in this case. So moving on, we'll compare the performance of these methods for some other applications. So our project that this method was developed for a European Union project called Admire, where the idea is to take user-submitted videos or user-submitted live streams where observers would be extracted from their background and then composited into a studio broadcast. So there's use for a style transfer method in this case because you would want the user image to look as if it's being filmed with the same camera as the broadcast image. So in this case, we compare our method to the same methods that we compared for the experiment, and we also compare to the control, where the user image is simply extracted and then composited directly on the studio background. And this is a really difficult problem because the studio backgrounds are highly chromatic, but they're generally not the primary influence on what's lighting the anchor in the studio, which is really the color information that we want to apply to the user. So it looks like the user is lit by the same lighting and filmed by the same camera. But in the studio, the lights are going to be brighter coming towards the anchor than the lights behind them. And also there's probably very little reflection from either it's a big LED screen or it's a green screen. And the like really chromatic things you see behind them are not actually even there in the scene and don't actually have an effect. So for that to be our reference image, there's a lot of information there that we don't really want to use. So the way that we do this is we remove the background of the user image and we replace it with the studio image as well, so that the user and the studio reference have the same background. So then you have sort of a range of color information. It's not limited to just the color information of the anchor, which is problematic because you can get things where you're matching people's skin tones together directly. If it's mixed in also with the background color, you get a more robust result. And comparing ours to the control, you can see that it's a subtle difference, but our result, we believe, reflects better the shooting properties of the broadcast. And then if you take a look at the results of Grogan, they basically just match the user's skin tone directly to the background, or a prominent color to the most prominent color in the background that's the most similar to their skin tone, which is quite problematic. And you can see there's also Photoshop and Sabaleta, there's some skin tone shifts which are really not acceptable for this application. If someone is going on to a studio broadcast and they see that their skin tone is being misrepresented, or their clothing or something like that, they're not going to be very happy about that. But the results of Photoshop and Sabaleta, they do okay in comparison to Grogan, but we can see Grogan's not very good for this application. We've also extended the feature decoupling base to spatial texture information by decoupling different spectral bands from the power spectrum and applying them from a reference image to a source. However, we don't use it in the same way as the color and luminance transfer, since we basically judge the spectral properties of an image in a more, it seems we judge them in a more strict way than we do the color and luminance properties. So if you're matching to an image with more spatial information, you're going to end up with a result that's over sharp, or if it's less spatial information, you're going to end up with a result that's too blurry. However, what we can use it for is the digital simulation of optical filters, which is the example we showed here. So on the top row, we have a reference image and then a source image. In the reference image, they're images of the same thing, but in the reference, there's an optical filter applied to the camera, and in the source, the optical filter is taken off. So we use our method to simulate first that optical filter in the result, and then taking these three source images, we apply it, and you can see that there's a similar blurring effect. Another thing that we've done is to encode our transform as a 3D lookup table, which allows for a static transform to be derived from the method, which can be easily applied to video sequences in real time, making our method more integratable in standard color correction workflows. And finally, we've wrapped everything together in a demo software that will accompany our paper, which allows for the adjustment of all the modular properties of the method, like excluding different features and color channels from the transfer, which allows users to go outside of the recommendations that we've provided in the paper and see what works best in their case. And we also allow for cropping of the source and reference, which is what we're showing here, which can be very useful. For instance, in this case, if you have a bunch of extra black area from the night sky, I know it's very fast, but you can see how that has an effect on the result. This software also allows for lookup table export, as we mentioned, so that people can derive a transform and bring it into their color correction workflow, and also batch processing, so you can apply a correction to a sequence of video frames. We believe all these features will allow artists to easily explore our method on their own images, refine their results, and integrate them into different workflows. So, in conclusion, we presented a novel style transfer method based on the statistical methodology of Reinhardt. We've demonstrated the robustness of our chosen paradigm in comparison to others. We've validated it for a range of applications. We've developed a demo software for artists to use, so we're very excited for the future of the tool, and thankful to the project for providing a solid base for its development. And in the future, we hope to explore the use of other color spaces, since we don't know the most optimal color representation to make the transfer in, as it's sort of unknown what is the best possible color representation for any application. To transfer other image features could be an interesting expansion as well as the application of using the method to make smooth transitions between images to reduce display fatigue. So a result I think people have when they're using their computer all day is this thing called display fatigue, where they're changing frequently between different between images which affect their visual adaptation processes differently. But if we're matching these statistics, then there's less adaptation that needs to be done from one cut to the next. So we think this would be an interesting expansion as well. Here I have my references, which if we provide this presentation to you guys, you can look. And thank you for listening. You can contact us here and ask any questions that you have now if we have time.
Thank you very much, Trevor. We have time for a couple of questions.
I know there's not many of you, so it's a lot of pressure. Sorry, go.
I just have one curiosity. Well, you compare your results with other methods. Do you actually implement all these methods, or they use the software? Or?
So they all provided demo software. So all of the results I showed here were directly from the demo software provided by each of their authors. Yeah, and most of them provide it in a way where there's really not much leeway. There's not many parameters to move around, so it's really just a matter of taking their demo software and replacing their test images with your images. That's how it goes.
And the second question is, when you compare your results with the others based on the psychophysical experiments, and you talk about the accuracy score metric, I quite don't understand what is this metric about. How do you?
So it's, are you familiar with the Thurstone methodologies?
No.
Well, I don't know if I can explain them very well right now, but it's based on this Thurston Case 5 methodology for computing statistics for a 2 alternate forced choice experiment. So basically, what it tells you is if you had an accuracy score of 0, then in essence, if there were 2 methods, well, no, I can't explain it very well, but if you had an accuracy score of 0, you'd have basically just as many times that someone says the method is worse than another one as they say it's better than another one, from my understanding. So if the accuracy score is like 1.5, like we see with Grogan here, then on average, 1.5 times more people will choose Grogan over the other methods.
So it's a kind of relative metric between
subjects,
right?
Yeah, it's all about just the relative comparison between 2 alternate forced choice.
So I guess you will need a really big sample of people to get accurate.
Well, so we have the confidence intervals here, which are 95% confidence intervals. So yeah, once in the beginning, those are going to be a lot bigger, and they could cross the threshold of the 0 accuracy score. But as you get a larger and larger sample, you can reduce that size. And also, this describes the variance from one image to the next. So I know that's not really your question, but if you have larger error bars in that sense, then you have sort of less consistent method.
Thanks. If I may, in image comparison methods, there's a protocol for experiments, and the number is 15 to give you 95% confidence. So you don't really need that many people for confidence. Any other questions?
Yes.
Okay.
You have used some psychophysical experiments with observers.
Mhm.
Did you compute the MIOS, I mean the limit observer scores or not?
Yeah, so that's where these accuracy scores come from. So that's the first step, is to compute these matrices of mean opinion score. And yeah, accuracy score, from what I understand, is just another way of representing that.
So the correlation that you obtained is better in your case than in comparison with the others?
So the correlation.
Let me just, if I may. So the mean opinion score is for the type of experiments where observers have to score an image. They're given a single image and they have to rank it, or sorry, not rank it, score it. You know, from 1 very bad to 5 great. And then you can correlate those numbers with what your model predicts how good your image is. But these kind of experiments are different. These are experiments where the user has to compare two images and select one over the other. So here, what we are doing is, with these psychophysical experiments, we are saying which method the observer prefers. And that's measured by the accuracy score. So a positive accuracy score means that, or the highest accuracy score means that that method is preferred by observers most of the time over the other results. And the negative accuracy score means that that method, the results are usually not preferred over the others. So there's no correlation to analyze here.
The integral should be 0, right? I mean the sum of these values. I guess
I believe so.
it is, no? So the 0 would be that half of the time is preferred, half of the time is not, no, as you said?
Yeah.
I understand. So it means that overall it should add up to 0. Yeah, that is consistent.
Yeah. Any other questions?
All right. If there are no more questions, we'll thank our speaker once again. Thank you.
Thank you very much for coming. Really appreciate it.
Did you see